In this video, we're going to discuss topics of bond polarity and electronegativity. And in the previous examples, we looked at homogeneous diatomic molecules, such as something like Cl2. So we can draw the Lewis structure of Cl2 something like this. But what if we have a heterogeneous diatomic molecule? For example, if we look at HCl, we have a hydrogen and a chlorine, and we're going to form a covalent bond just like this. So in this particular case, we form the Lewis structure of HCl like this. In the Cl2 case, we have a nonpolar covalent bond because there is equal sharing of the two electrons contained in that bond because we have equal atoms on the left-hand side and the right-hand side. In the case of HCl, we have a polar covalent bond. And the reason this bond is polar is because we have an unequal sharing of the electron pair that's between the hydrogen and the chlorine. And we can explain this unequal sharing using the concept of electronegativity. And electronegativity can be defined as the ability of an atom to compete for an electron versus another atom to which it is bonded to. And when we look at the electronegativity trend, remember that electronegativity increases as we go from left to right in the periodic table, and it decreases as we go from the top to the bottom of the periodic table. And if we look at the relative electronegativity values, they are less than 2 for metals. They are roughly around 2 for metalloids, and they're typically greater than 2 for nonmetals. So we can kind of use these general trends to see how bad a particular atom wants that electron. So if we come back to our HCl example here, we called this a polar covalent bond because there's unequal sharing of electrons. The reason there's unequal sharing of electrons is because the chlorine atom is more electronegative than the hydrogen atom. As a consequence, if we look at this, our electron will spend more time on the chlorine. And this will give a partial negative charge on the Cl. And this is going to make it polar, just like a magnet. You have a positive end and a negative end. So we can look at other molecules. For example, if we have CO2 which is going to have a Lewis structure like this. Here we have our carbon in the center, and think of this kind of like a physics problem where we look at vectors. You have electrons pulling this way because the oxygen is going to be more negative, the carbon is going to be positive, and each of these vectors are going to be equal and opposite. So here we have an equal sharing. So we can call this a nonpolar covalent bond, or a nonpolar covalent molecule. Whereas if instead of having CO2, we have a molecule where sulfur is bonded on the right and oxygen on the left, here we're going to have an unequal sharing of that electron because sulfur is going to be less electronegative than oxygen, because as you go down in the periodic table, the electronegativity is going to decrease. So our vector over to the right, our negative charge, is not going to be nearly as strong as the vector over here on the left. So as a consequence, the electrons are spending more time on the oxygen. And when these bonds form, when these covalent bonds form, we have an overlap of orbitals. When orbitals overlap, the electron can pretty much move around. The electron can move around throughout the entire system. We're not constricted to just having the electron on the oxygen atom or the carbon atom or the sulfur atom. That electron can move throughout the entire system. And the electronegativity is going to tell us how bad an atom wants a particular electron, and as a consequence, if we have a more electronegative atom, the electrons are going to reside on that atom more in this entire system for the molecule. So here we have an unequal sharing, and the molecule over here on the right we can say is a polar covalent molecule. So in the next video, what we'll do is we'll try to come up with some type of way that we can categorize ionic versus covalent bonding and look at the similarities and differences between those types of bonds.